Okay, Chapter 2 in the OTCO Workbook. We start to get into a little bit of the math that you're going to need to know how to do well in this class and to do well on an exam. So I wanted to cover a few of these examples for you and show you how they're done. Hopefully this is just a refresher for you. So let's go ahead and start with average. So calculating an average is pretty straightforward. We add all of these numbers together. So 10 plus 15 plus 17 plus 33, when I add them together, I get 75. And then we divide the sum by the actual number of values that we added together. So in this case, 75 divided by 4 gives us an average of 18.75. So hopefully that one was pretty easy for you. The second one that I'm going to get into is these dimensional analysis problems. And they didn't ask you to solve any of these. They just wanted you to determine whether or not this was a way to solve or to set the problem up to solve for what you were trying to determine. So in this case, in this example, would this be a way to figure out gallons per minute? So I wanted to do this one for a couple reasons. Obviously to show you the dimensional analysis setup, and also to show you what I'd mentioned in the PowerPoints about dividing fractions. So another way to think about this problem, or another way to write it, would be like this. 2,800,000 gallons per day. So we can write that actually as a fraction. And it would look like this. 2,800,000 gallons. And remember in the PowerPoint I mentioned that anytime you see the word per, that's kind of a tip-off that you can write that as a division problem. So 2,800,000 gallons per day is really 2,800,000 gallons divided by 1 day. And then at the bottom of our division problem, we have 1,440 minutes per day. So if we wrote it like this, it would be kind of confusing, but this would be correct. 1,440 minutes per 1 day. But remember in the PowerPoint I mentioned that when you are dividing by a fraction, what you're really doing is multiplying by the inverse of that fraction. So another way to write this problem would actually be 2,800,000 gallons divided by 1 day times the inverse, or 1 day divided by 1,440 minutes. And now when we're multiplying fractions like this in a story problem, we can cancel out like units of measure. So in this case, we could cancel out days. We have a day in the denominator on this side and a day in the numerator over on this equation, so they actually cancel out. So we could basically wind up with 2,800,000 gallons divided by 1,440 minutes. So our answer would actually be in gallons divided by minutes, or gallons per minute. So yes, that would actually be correct as a way to set that problem up. Percentages and decimals. If you don't, hopefully you remember this from high school math, but 100% is equivalent to 1, or 1.00. Think about it this way. If you had a pizza and you had 100% of the pizza, you would have one whole pizza. So if you only had half of a pizza, let's say your kids came in and ate half of the pizza while you were in the shower, then you would only have one half of the pizza, or 0.50 pizzas, or 50%. So as you go through all those problems, remember that 100% equals 1, or 1.00, and then percentages are expressed as decimals. So 50% would be the equivalent to 0.5. Following, if you had, say, one slice of pizza, you would have 12.5% of that pizza left, or 0.125, and so on. Continuing, solving for the unknown, which is, again, another set of problems where they don't actually want you to solve the problem. They just want you to go through the steps required to solve the problem. So let's take a look at this problem here. Remember, with our transitive property in algebra, we can do anything to an equation as long as we do it to both sides. So in looking at this equation, the very first thing that I want to do is, in order to get the variable on one side of the equation, is I'm going to try to eliminate the fraction on the left-hand side. So I'm going to do that by multiplying both sides of the equation by 5 over 1, or 5. And what that's going to do for me is get me to 7 times 4 equals 3 times 5 over x times 2. The next thing that I'm going to do is multiply both sides of this equation by x times 2 over 1. So now x times 2 cancels itself out on this side of the equation, and what I'm left with is x times 2 times 7 times 4 equals 3 times 5. Now, finally, to get x by itself, I'm going to divide both sides of the equation by 2 times 7 times 4. So when I'm done, I have x on one side of the equation and 3 times 5 divided by 2 times 7 times 4. So remember, with the transitive property in algebra, you can do anything that you like to manipulate an equation as long as you do it to both sides of the equal sign. Okay, moving on to ratios and proportions. One of the questions that you had to solve was asking are these numbers proportional or are they equivalent? And in order to solve these, you want to cross multiply. So are these numbers proportional? Well, let's go ahead and cross multiply. 140 times 10 would be 1,400. Is that equal to 110 times 15? Well, 110 times 15 is 1,650. Are they equal? No, they're not. So, not proportional. Moving on to conversions. Converting 7 cubic feet per second into gallons per day. So let's go ahead and set this problem up. Remember, 7 cubic feet per second, I can rewrite that as 7 cubic feet per, means I want to divide, divided by 1 second. Now I have some conversions that are on the formula sheet that came with my textbook, or that you can look up online. How many cubic feet in a gallon? There are, or how many gallons, I'm sorry, in a cubic foot? There are 7.48 gallons in 1 cubic foot. And then finally, I want to find gallons per day. So how many seconds are there in a day? Well, I happen to know that there are 86,400 seconds in a 24-hour day. So my problem sets up like this. And now, as we've done in a couple previous problems, I can cancel out like units of measure. So let's see here. I can cancel out cubic feet. I have cubic feet in the numerator and cubic feet in the denominator. Those cancel out. Seconds in the numerator cancels out seconds in the denominator. So when I multiply this out, I'm going to be left with an answer in gallons over days, or gallons per day. So that's how I would set that problem up. And if I multiply it out, 7 times 7.48 times 86,400 would give me 4,523,904 gallons per day. And then finally, some problems with linear measurement and then measuring area and then volume. So hopefully this all should be pretty straightforward for you. Let's say that we have a square that is 4 feet by 4 feet. Obviously, if we wanted to determine the perimeter, we know it's a square, so all of the sides are equal distant. Perimeter would be 4 plus 4 plus 4 plus 4, 16 feet. Area would be length times width, or 4 times 4. 4 feet times 4 feet is 16 feet squared, and I would highly recommend getting in the habit of writing it like that, 16 feet squared, or 16 square feet. And then, of course, volume, 4 feet, 4 feet, 4 feet, length times width times height, or 4 feet times 4 feet times 4 feet equals 64 cubic feet, or 64 feet cubed. So that is volume, area, and then of course just the perimeter. And now let's say that I knew the area of one side of the square, so we're going to just say, let's say we knew the area of one side of the square. And we're just going to assume for the purpose of this problem that this was, let's say, a rectangle. So I know length times width, and I know the volume, and I want to determine height. So let's say I know this formula, length times width times height equals volume. And let's say I knew the volume was 64 cubic feet, and I knew the length was 4 feet, width was 4 feet, but I did not know the height. So 4 times 4, 16 feet squared times height equals 64 cubic feet. Remember from the last problem about trying to get isolating our variable on one side of the equation, we can rewrite this equation like this. H, remember, if we divide both sides of the equation by 16 square feet, we can get this variable on one side. So this is going to wind up looking like this, 64 feet cubed divided by 16 feet squared. Now, I touched on this briefly last week, but this is my first example of this, and I would highly recommend you get in the habit of doing problems like this. If you remember, this should have been probably pretty basic high school algebra, and I'm 51 years old, so I probably took high school algebra 36 years ago. I have taken a few college classes in the meantime, but I had to refresh my memory on this. But when you are looking at numbers with exponents, so let's say x cubed, and we want to divide by x squared. When we're dividing exponents, or numbers with exponents, we subtract. So 3 minus 2, and that tells us that our answer is going to be in the exponent of 1. So when I divide 64 by 16, I get 4, and I get 4 feet to the first power because I subtracted exponents. And then, of course, 4 feet to the first power is just 4 feet. So I'm able to determine, if I'm given the volume and 2 of the dimensions, or an area in square feet, what the 3rd dimension or the depth is. So yeah, you can do these problems without remembering this rule, but if you write things down this way, I highly recommend it, and I think the math as we go along will be easier for you. Conversely, if you're multiplying 2 numbers that have exponents, so let's say x to the first power times x squared. When you're multiplying numbers with exponents, you add them together. So instead, this would be 1 plus 2. So our answer would be x to the third power, or x cubed. And this is all the farther you need to go with exponents, but I think it's an important principle to understand that when you're multiplying area, which is, say, typically expressed in square feet, if you're multiplying by a third measurement in linear feet, linear feet times square feet is going to give you an answer in cubic feet. And I think that'll come in handy. So that's all I've got. A little video to help you with some of the math in Chapter 2.